Okay, so we all know by now, right, that just cutting emissions, well, it's not going to cut it, is it? If we're serious about hitting those, kind of crucial climate targets, like 1.5 degrees Celsius,
Yeah.
or maybe even 1 degree.
Yeah, more and more, the science is really pointing towards this need for active carbon dioxide removal, actually pulling it out of the atmosphere.
Right. And it's not just a little bit either.
Yeah.
We're talking like potentially 500 gigatons of CO2 this century.
Yeah, and some estimates go even higher, up to like 1,750 gigatons.
It's a huge challenge.
It's a truly staggering scale, and I think that's why the research we're going to be looking at today is so vital.
Yeah.
This paper, Techno Economic Insights and Deployment Prospects of Permanent Carbon Dioxide Sequestration in Solid Carbonates.
Catchy title.
It does what it says on the tin.
Yeah.
It gives us some really, insightful techno-economic insights into how we can permanently sequester carbon dioxide.
So, and this is a key difference, right, between this and some of the other kind of carbon capture methods, is this idea of it being permanent. We're not just kind of storing it and hoping for the best.
Exactly.
We're actually locking it away for good.
And that's really, front and center, this concept of permanence. And we're talking about, CO2 being chemically bound in these stable carbonate minerals, potentially for thousands of years. If you contrast that with, storing CO2 underground, there's always this uncertainty, right, about leakage in the long term. Even, some of the natural carbon sinks we have, they can be vulnerable to things like wildfires,
right?
Releasing stored carbon back to the atmosphere.
So for you, dear listener, our mission in this deep dive is to really kind of get under the hood of mineralization. We want to explore the different ways we can turn CO2 into rock, the kind of cost and energy involved, and crucially, whether this can be scaled up to make a real dent in the climate problem.
Yeah. And as the paper lays out, there are three main routes to mineralization. In situ mineralization, which they call MinIN, ex situ, MinEx, and enhanced weathering, which is EW. Figure 1 in the paper, actually, it's a really helpful visual overview if you want to kind of picture these different approaches.
Yeah, we'll put a link to the paper in the show notes for you to, peruse at your leisure. Okay, so let's start with the big picture. Even if we imagine a world where everything's running on renewables,
right?
Why is this idea of removing CO2 and specifically mineralization still so important?
Well, the paper argues that because of our historic emissions and the delays we've had in taking action, we've likely exceeded the kind of safe atmospheric carbon budget.
Right.
So even with a full transition to renewables, we still need to actively draw down that excess CO2 to get back to safe levels. And that permanence that we talked about, right, that's a really key factor here. I mean, it points out the inherent risks with something like geological storage, which, involves injecting CO2 into deep underground formations, potential leaks, there could be seismic events, integrity failures.
Right.
The idea of locking CO2 away as a solid is, it's very attractive.
It sounds more secure somehow.
Right.
Like if it's, a solid thing, it's not going anywhere.
Exactly. And then natural solutions like, forests and wetlands, they're important.
Right.
But they do have limitations in terms of capacity, how much carbon they can realistically sequester. And then, there are the questions of their long-term stability. Are they really permanent sinks?
Okay, so permanence is the key takeaway here. Let's dive into these different methods that the paper outlines. The first one's in situ mineralization, or MinIN. So we're talking about turning underground rocks into CO2 sponges. How does this actually work?
Well, you dissolve CO2 in water, and then you inject this CO2-rich water deep underground into specific types of rock formations.
Right.
Primarily basalt or peridotite. And these rocks naturally contain minerals that react with the dissolved CO2 to form solid carbonate minerals. So the CO2 becomes essentially part of their rock structure.
So it literally turns to stone.
It really does, permanently locked away beneath the surface.
Oh, wow. Now, the paper mentions a project called CarbFix in Iceland.
Yes.
That's a real-world example of this happening right now, isn't it?
It is, and it's actually been going on for over a decade.
Wow.
It's linked to a geothermal power plant.
Right.
It really demonstrates the feasibility of this process and the speed.
So how quickly can this happen?
In basaltic rocks, 80 to 95% of the injected CO2 can mineralize in 1 to 2 years.
Wow.
That's remarkable.
That is really fast.
Compared to what we think about with, geological storage, we're talking centuries.
Right.
This is 1 to 2 years. And that actually It means we don't have to worry as much about the long-term stability of the caprock.
Right. And just to explain to listeners who might not be familiar, the caprock is kind of the layer of rock that sits above the storage reservoir. And it has to be impermeable to prevent the CO2 from escaping, right?
Exactly. That's a major concern with, traditional CO2 storage. But with this rapid mineralization that we see in basalt, it sidesteps that issue to a large extent.
Okay. So, and in terms of where this could be done, the paper talks about large igneous provinces,
Right.
or LIPs,
Mm-hmm.
and flood basalts. And I mean, Figure 2 shows us that these are distributed pretty much globally, suggesting we could find these sites on every continent.
Yeah, potentially. I mean, it is vast, that potential. But
Yeah.
but the paper does also point out a potential bottleneck,
Okay.
which is the amount of water needed for the process. Because to dissolve the CO2, you need water.
Right.
But there is some promising research exploring the use of seawater.
Okay, so that would alleviate some of the freshwater concerns.
Absolutely.
That's good to know. The study also gives us some cost estimates for MINM starting in 2030, both for onshore and offshore projects,
Mm-hmm.
as well as the anticipated final energy demand. We'll link to those figures in the show notes as well. Okay, let's move on to the second route, ex situ mineralization, or MINEx.
Mm-hmm.
And this sounds a bit more like an engineered process. We're not injecting things underground.
Exactly.
We're using reactors, right?
Right. This is where we take suitable feedstock, which could be rocks like olivine and serpentine, or even industrial waste that contain magnesium or calcium,
Okay.
and react them with CO2 in a controlled environment.
So instead of bringing the CO2 to the rocks, we're bringing the rocks to the CO2.
You got it. And the study specifically focuses on what's called a direct aqueous carbonation reactor design,
Right.
where you're basically dissolving the CO2 in water and then reacting it with the feedstock.
Okay. And the feedstock, that needs some pretreatment, right?
It does. Grinding's necessary for all feedstocks to increase their surface area and make the reaction more efficient.
Right.
And for serpentine, there's an additional step of magnetic separation to remove something called magnetite, and then a thermal treatment as well.
Okay. Now, what I find really interesting about MINEx and what the paper highlights is its potential to use industrial solid wastes.
Yeah.
Like steel slag or cement kiln dust, red mud.
Mm-hmm.
So we're not just capturing carbon, we're also finding a use for these waste materials.
Exactly. It's this, idea of a circular economy.
Right.
That we can use these waste products and actually, do something beneficial with them.
It's a fantastic 2-for-1 if it worked out.
Yeah, but it's important to note that the paper assumes these wastes are available without additional cost or energy input, because otherwise you'd have to factor in the energy needed to collect and transport these wastes.
That's a good point.
Yeah.
What about water usage for MINEx?
Well, the initial water demand might seem high, but direct aqueous MINEx actually has the potential for very high water reuse rates.
Okay.
We're talking up to 99.96%.
Whoa.
So that really minimizes the net freshwater demand.
Right. That's good to hear. The paper also goes into the specific temperatures and pressures involved in the reactors.
Mm-hmm.
And then what about the chemistry behind it? There's mention of equations 1, 2, and 3.
Right. And essentially what those equations describe is how minerals that contain, magnesium or calcium silicates or oxides or hydroxides react with the CO2 to form stable, magnesium or calcium carbonates.
Right.
And then other byproducts like silicon dioxide or water.
Okay, so basically the CO2 molecule bumps into certain elements within the rock like calcium or magnesium, and they kind of grab onto the CO2 and form a new solid compound. That's the carbonate mineral.
Exactly.
And that traps the carbon.
Yeah. And the paper provides cost estimates for MINEx as well, starting in 2030, using different feedstocks, serpentine, olivine, steel slag. And it also, looks at the final energy demands associated with each feedstock. And then there's this really interesting mention of potential valuable byproducts, especially in the cement industry.
Right.
Which kind of hints at this idea of CCUS, right? Carbon capture, utilization, and storage.
Yeah. Yes. You're not only capturing the carbon, but you're creating something useful in the process.
Exactly.
Very cool. Okay. So the third route is enhanced weathering, EW. And this sounds like we're kind of getting nature to help us out a bit more directly.
Right. It involves spreading crushed calcium and magnesium-rich rocks, things like basalt, on land. And this study specifically looks at cropland.
Okay.
The idea is to massively increase the surface area of these rocks,
Right.
which can then naturally react with CO2 in the atmosphere and rainwater.
Hmm.
And that accelerates the natural weathering process that already removes CO2 and forms carbonates.
So we're kind of speeding up a natural process by grinding up rocks and spreading them around. What kind of things influence how much CO2 gets taken up through enhanced weathering?
Well, the rate of carbon dioxide removal depends on a few things. How much rock you spread, obviously.
Right.
The dissolution rate, so how quickly those rocks actually dissolve.
Okay.
The CO2 sequestration potential of the specific type of rock you're using. And then the grain size.
The grain size. Okay, so smaller particles, that means more surface area, right?
Yeah,
And faster weathering.
Yeah.
But I seem to remember reading that there's a bit of a catch there. If the particles are too fine, there can be health risks. Okay.
That's a crucial point. Finer particles, they do weather faster,
Right.
but there are concerns about potential respiratory health issues if the particles are ultrafine.
Right.
So the study it makes an assumption that you'd be using a grain size of around 10 millimeters
Okay.
to balance those two things, weathering efficiency and potential health risks.
That makes sense.
Right.
And it also provides cost and energy demand estimates for EW starting in 2030.
Yeah, and it's interesting to note that EW is the only option out of these three that primarily relies on electricity,
Okay.
for handling the rock, spreading it, and the total energy demand is quite sensitive to how far the rock has to be transported.
Right. So the logistics are important here.
Mm-hmm.
Okay, so we've covered the three main methods for mineralization. Let's kind of zoom back out again. What about the global potential for actually deploying these techniques? Where in the world could we see this happening at scale?
Well, the paper includes some figures that map this out.
Mm-hmm.
For Maine, South America seems to have the highest total and annual potential.
Right.
For Maine-X, using industrial waste, regions like South Asia and Sub-Saharan Africa, they're projected to become major contributors.
Okay.
And then EW, the potential there is closely linked to the availability of cropland.
Okay.
So places like Sub-Saharan Africa again, North America, and South Asia.
Okay. And what about the energy demands for each of these options?
Yeah.
I mean, we've talked about them individually, but how do they compare when we think about, the bigger picture of our energy systems?
Well, the figures show us that EW generally has the lowest total final energy demand because it mainly relies on electricity.
Okay.
Mine also has relatively low energy intensity. And then Minex, particularly when it's using mined rock as the feedstock, that tends to have a higher energy demand because of the energy needed for the mining, the pretreatment, the reactor operation, and importantly, the direct air capture of the CO2.
Right.
So, that's something to factor in.
Yeah, definitely. And then there's the all-important question of cost.
Right.
And it looks like things could become quite competitive, as we move further into the century.
Yeah, the high initial costs for things like the direct air capture, that makes Mine and Minex relatively more expensive than EW in the short term.
Okay.
But the paper projects that costs for all mineralization options can fall below 100 euros per ton of CO2 removed by 2050.
Wow, that's really significant.
It is, and Mine is expected to become cost competitive with EW around that time, mainly because of the anticipated reductions in DDA costs.
Okay.
And Minex using industrial waste.
Right.
Well, that's projected to be more economically attractive than using mined rock because, you're avoiding the costs of mining and handling that feedstock.
Okay, so that makes a lot of sense.
Yeah.
The paper also briefly mentions technology readiness levels, or TRLs, which kind of give us a sense of how mature these different approaches are.
Right. So EW and Mine-N, they're generally considered more mature technologies.
Okay.
With TRLs of like 8 or 9.
Okay.
Because they build on well-established practices in things like mining, drilling, fluid injection.
Right.
Minex, and in particular the reactor technologies for efficient carbonation, well, they're at a slightly lower TRL, maybe 5 or 6.
Okay.
Because those large-scale plants, they're not widely deployed yet.
Right. So if we imagine scaling up mineralization to meet a significant chunk of our, CO2 removal needs, say 60% of the projected demand for hitting those 1.5 and 1 degree targets, what kind of impact would that have, globally, economically, energy consumption?
Well, the study estimates that meeting 60% of the projected CDR demand through mineralization, that could require something like 0.06% up to 0.21% of global GDP in 2070 for the 1.5 and 1 degree targets, respectively.
Okay.
On the energy side, we're looking at an additional primary energy demand, maybe up to 2.5% and 8.6% in 2070.
Right.
Again, for those same climate targets.
Okay.
But those are significant numbers.
Yeah.
But the paper does point out that, with the expected growth of renewable energy, this additional demand might be manageable.
Okay, so in the context of a decarbonizing energy system, it might not be as daunting as it sounds initially.
Right. Exactly.
And the paper also touches on some current challenges for each method.
Yeah. So for minans and direct aqueous minics, the potential reliance on fresh water is a concern.
Right.
Given, water scarcity issues around the world. So research into things like using seawater for Mainen and improving water recovery rates for Minex,
Right.
they're going to be crucial.
Yeah.
For EW, it's about managing that potential for ultrafine particle dispersion
Right.
and the associated health risks. And then for Minex, it's about, making sure you're only using non-hazardous waste materials as feedstock.
Okay.
And ensuring that there's actually enough of the right kind of waste available in the first place.
Right. That's a good point. It's all about, thinking about the availability of these resources.
Mm-hmm.
Okay, so I want to circle back to that core benefit of mineralization that we talked about at the beginning.
Right.
This idea of permanence.
Mm-hmm.
Why is this so important when we think about, the kind of the broader picture of carbon dioxide removal?
Well, I think the permanent nature of CO2 sequestration in carbonates, it's just a fundamental advantage over other approaches.
Okay.
And the paper contrasts it with, geological sequestration,
Right.
where the risk of leakage and the need for long-term monitoring, they're ongoing concerns.
Right.
And compared to, some other CDR methods that might be reversible,
Right.
mineralization just offers a much more secure and long-lasting solution
Right.
for large-scale carbon removal.
Mm-hmm.
And it provides that certainty that the captured CO2 won't be going back to the atmosphere in the future.
Right. So you can really see why that permanence is so appealing, especially when we're talking about, these really long-term climate solutions.
Exactly. And I like to think of it, it's like trying to keep air in a balloon with geological storage, right?
Mm-hmm.
You have to make sure there are no leaks.
Yeah.
But with mineralization, it's like that air's turning into part of the balloon itself.
Okay.
It's fundamentally changed and it can't escape easily.
So basically what the paper is telling us is that mineralization has the potential to be a really crucial technology for sustainable and truly permanent carbon dioxide removal.
Yeah, and it concludes that while there are definitely challenges, that we still need to address, mineralization offers several viable pathways for permanently removing CO2 from the atmosphere,
Right.
each with its own, costs, energy requirements, global deployment possibilities.
Right.
And importantly, those projected costs, they're expected to become more and more competitive over time,
Right.
which makes mineralization, a really significant contender in the portfolio of climate change solutions.
Okay, well, this has been a really fascinating deep dive into techno-economic insights and deployment prospects of permanent carbon dioxide sequestration in solid carbonates.
Catchy.
It really does. It really does. It gives us a real sense of the potential, but also, the complexities of locking away CO2 for good. So a final thought for you, the listener. As you go about your day, consider those trade-offs we've discussed. The costs, the energy use, that really important factor of permanence, and the scalability of these different approaches.
Mm-hmm.
What role do you think these permanent solutions like mineralization should play in our global efforts to tackle climate change?
Yeah, it's something to ponder.
We encourage you to delve deeper into this research and the whole field of carbon dioxide removal, which is just, it's such a rapidly evolving space right now.
It really is.
There's so much happening.
Yeah.
So thank you for joining us.
Thanks for having me.
And until next time, keep diving.